When a massive industrial motor spins up to drive a heavy steel shaft, you're witnessing an immense application of raw physical torque. Delivering that kind of continuous mechanical force requires a volume of electricity far beyond what you use in your home. A television or a washing machine runs perfectly well on a single, standard line of alternating current. However, a single line of alternating current oscillates back and forth, meaning the power delivery actually drops to zero at the crossover point of every cycle. For a massive motor under heavy load, these gaps in energy prevent the consistent torque needed to keep a heavy shaft turning. This is why heavy industry relies on three-phase power. By delivering current across three separate overlapping lines, labeled L1, L2, and L3, the system ensures that as one phase drops, the others are at peak delivery, providing a constant energy flow. The volume of voltage and high-intensity current traveling through these lines is lethal, flowing directly to the equipment. To harness this power, we must engineer a physical and electrical barrier between the human operator and these high-voltage lines. Building that barrier requires us to solve three specific engineering problems. First, we need a way to turn a lethal high-voltage system on and off without ever physically touching the circuit. Second, we must defend the entire electrical circuit against a catastrophic short circuit that can flood the system with energy instantly. Third, we have to protect the motor itself against mechanical failures that cause current to rise slowly, generating intense heat over several minutes. The standard three-phase motor wiring diagram acts as the integrated framework designed to address these three variables in a single, repeatable circuit. By building this topology from the ground up, component by component, we can see the exact logic behind every layer of defense in the circuit. Because of the massive current flowing through lines L1, L2, and L3, installing a manual light switch directly on these wires would put an operator at risk of a fatal arc flash. We avoid this danger by breaking the direct line to the motor and inserting the contactor. A contactor functions as a synchronized bridge, using a single mechanical action to close three independent high-voltage paths at once. If we look inside the contactor, we see two entirely separate systems. There are the three high-voltage contacts, and sitting completely isolated from them is a tightly wound wire coil on a separate 24-volt circuit. When you press a button at a control station, you apply 24 volts to that coil. This causes the energized coil to become a localized electromagnet. That magnetic field pulls the high-voltage contacts closed. The gap is bridged, and the massive three-phase power flows to the motor. When you cut that 24-volt power, the magnetic field collapses instantly. The heavy contacts snap open, severing the motor's power supply. This achieves electromechanical isolation. We can safely manipulate lethal high voltage from a distance, using nothing more than the magnetic field of a low-voltage coil. But isolation does not protect against a sudden fault. If crossed wires create an instantaneous short circuit, a massive flood of current will tear through the system. The contactor cannot stop this volume of electricity. The heat of such a surge would simply melt its internal components and fuse the contacts permanently shut. To prevent this, we move to the top of our schematic, placing three fuses at the very origin of the power supply. Zooming in on one of these fuses reveals a precisely calibrated strip of metal bridging the electrical path. This is a sacrificial element. When hit by an extreme, instantaneous spike of current, that internal wire overheats and burns through in milliseconds. By vaporizing its own internal wire, the fuse creates an absolute physical break in the circuit, ensuring the surge never reaches the downstream equipment. As this acts as a permanent physical destruction, the system remains offline until an operator clears the short circuit and manually replaces the dead fuses. Fuses provide a high-speed hard stop at the border of the circuit, destroying themselves to block catastrophic surges. While fuses handle sudden electrical spikes, they respond differently to a current increase that occurs as a slow, gradual crawl. Consider a heavy industrial conveyor belt powered by our three-phase motor. If a heavy object falls and jams the belt, the machinery stops moving. The motor continues trying to spin, drawing more and more electricity to force the unmoving load forward. Our high-speed fuses will not trigger here. The steady climb in current is too slow to snap the sacrificial wire, allowing the motor to eventually melt from the inside out. To solve this, we add our final component, the overload relay, placed right before the motor. This relay continuously monitors the thermal increase of the circuit. While the motor glows increasingly red, the graph on the right tracks the slow upward trajectory of the electrical draw. Once that slow climb crosses a specific threshold, the relay recognizes the jam and trips, opening the circuit and cutting power. Unlike a fuse, an overload relay does not destroy itself. Once the mechanical jam is cleared and the internal mechanism cools down, the operator simply resets the device. This completes our bifurcated defense. The overload relay provides slow, sustained thermal protection, while the fuses stand guard against sudden catastrophes. Looking at the entire wiring diagram from top to bottom, we can see the exact logic of the complete system. Three-phase power enters from the top, delivering consistent energy. The flow hits the fuses, blocking instantaneous spikes. Electricity then reaches the contactor, halting until it receives a magnetic command. Finally, it passes through the overload relay, ensuring a physical jam doesn't overload the motor. This sequence is a rigid architecture dictated by the physics of power distribution and thermal dynamics. Reading an industrial wiring diagram is ultimately an exercise in recognizing this multi-layered system designed to safely cage and direct extreme raw power.